Okay, so we're going to look at Lewis dot diagrams, which will lead into Lewis dot structures. All right, so Lewis dot diagrams are very convenient, easy ways to show the valence electrons. All right, so to do that, you start out with the symbol and the number of valence electrons it has. So if we look at hydrogen, its atomic number is 1. It only has 1 electron. Therefore, that electron has to be the valence one. You can draw it any number of ways. You could start it at the top. You could rotate it because that comes in handy with the other Lewis structures that we can build. And it can be anywhere that you really need it to be. What I want us to get in the habit of doing when we're doing the diagrams is starting out in the 12 o'clock position like this one. But know that we can use it in any way, orientation to get the job done when we're making actual molecules out of it. So helium, atomic number 2. 2 protons, 2 electrons. It's on the first energy level, just like in the Bohr diagram. That means that it has 2 and only 2 valence electrons, and it's at its max. So helium, instead of rotating here and here, we're going to put them together because helium is a noble gas. When we show the electrons together like that, they're really not going to be available for bonding. And helium, same way. You can move those double dots anywhere you want to, however you need to make it happen. Now, like the video from Polikoff, where he says that helium and neon don't react with fluorine, you're not going to be making a lot of helium Lewis dot structures because it doesn't react with much of anything. It's one of those true noble gases, very inert. Okay, so let's take a look at something that's on row 2. All right, lithium, it's on row 2 of the periodic table. All right, it's in group 1, so it has 1 valence electron. All right, so we can put the lithium any way we want to, and I'm not going to go through all the iterations there. When we go to beryllium, beryllium's row 2, column 2, group 2, whatever you want to call it here. How many valence electrons does it have? 2, right? So unlike helium, beryllium, we're going to spread them out. Okay? And when you do the different iterations, you just keep them spread out. Right next to each other, like the arms, if we start at the time at 3 o'clock, we go down to 6 o'clock. You want to keep them together because that'll help you figure out the shape of a molecule in the future. Okay? Aluminum, it's in group 13. So how many valence electrons does it have? All right, so someone said 13.
Oh, 3.
And 3. It's actually 3. It's the ones digit. And because if you look on our NIST, you look at aluminum, it's element number 13. It's in group 13 or group 3A. So 1, 2, 3. All right, and like I said, if you go through and you need to flip it somehow, you just move the dots. So something like germanium. What group's it in?
Uh, 14.
14. So how many valence electrons? 4. Right? Now, really can't spread these around too much, but you can move them to the edges. Like I said, there are many iterations. Sometimes when you're drawing these Lewis structures out, it works out better if you put them at the corners. So you can do it, put it at 12, 3, 6, and 9. You could do it like 1030 and then 230 or 2 or whatever, 10 and 2, whatever you want, however you want to visualize that, but it can be moved around. Then it gets a little different when we go to, let's look at nitrogen. Nitrogen, what group's that in?
15.
15. How many valence electrons? 5. So 1, 2, 3, 4, 5. Now, what do you notice about nitrogen and something like helium? What does it have in common with helium here? Yeah, 2 valence electrons at the top, 2 valence electrons paired up. So this one, we can move it around. If we needed to draw it like this, we could. All right? But the key here is when we get to the structures, we're not going to form a bond here most times. There are certain things that are very reactive that will actually cause it to lose some more electrons or something like that. But generally speaking, that's a non-bonding site. All right. And you look at sulfur. Sulfur, good old S. Right? So sulfur is in group what? 16. So 6 valence electrons. 1, 2, 3, 4. It's a little bit hard to see. I'm going to get that bigger. All right. So sulfur has 6 valence electrons. It has 2 electrons that are paired up. Or 2 pairs of electrons, I should say. And 2 single ones. And then you look at something like bromine. Now let's look at fluorine, since that was in the video we saw earlier. All right, fluorine. It's in group what? 17. How many valence electrons? 7. Okay, 1, 2, 3, 4, 5, 6, 7. And then let's try a noble gas. Krypton. For all you Superman fans. What group's it in? 18. How many valence electrons? Yeah. 1, 2, 3, 4, 5, 6, 7, 8. Remember the octet rule? No. Okay, so the outer energy level, valence energy level, is considered full when you have 8. That's the reason why the gases like neon, krypton, argon, xenon, and radon are noble gases. Do you see any single electrons? No, they're all paired up. It really has no reason to react with anything. It has all the electrons it needs. And if you remember the trend going across the periodic table, the atomic radii gets smaller as you go across because it's holding on to those electrons even tighter. Makes it harder to break these electrons free. Okay?
How come on the 15, row 15. The top.
Oh, group 15? Yeah.
Yeah, why is that 5?
Why is group 15 5?
Yeah, why is that 5 electrons?
Okay, so if you look at, let's look at nitrogen, okay? Atomic number 7. Let's go back to the Bohr diagram real quick, right? And right now, all I'm going to do is just put the nucleus with the symbol in it. First energy level for nitrogen. The first energy level can only hold 2 electrons, okay? Nitrogen's on the second row, which means it has 2 energy levels. 7 electrons minus 2 electrons is 5 electrons. So we have to place 5 electrons. The first energy level is full. We have to place it on the second. I have 5 on the second. I've placed all the electrons. And then it's the outside energy level that is the valence. So whatever ring that has electrons is its valence on the outside, furthest from the nucleus. So if you look at this Bohr diagram, and then you look at what the Lewis dot diagram looks like, you can see where we got the dots at. Okay? And what the Lewis dot diagram allows us to do is skip all the rings and everything else. Because when we get to the point where we're using Lewis dot diagrams to make Lewis dot structures, we don't want to have to draw out the Bohr model every single time. A Lewis dot diagram takes care of everything we need. We only need to know how many valence electrons it has to make a structure. Because this can combine, if I have 3 of these and I have 1 of these, I can make a compound, right? Hydrogen, hydrogen, hydrogen. And this is what we would call a covalent compound, because they're going to share these electrons. If I were making an ionic compound, like with lithium and nitrogen, I would know that I need 3 lithiums. And what's going to happen is each of the lithiums is going to lose an electron and become positively charged. So we'll have 3 positively charged lithiums plus 1 3 minus charged nitrogen, and it will form a compound. Okay? And they'll be attracted to each other, and we end up with Li3N. This one is NH3. So that's where we're going with it. It helps us visualize what's going on quickly. And then you get to the point where you don't need the Lewis dot structures to make this happen. You're looking at the periodic table and realizing what the patterns are. But this helps you visualize it to begin with, help put you in perspective, and it's really handy when we're doing stuff like this to start getting an idea of what shape the molecule would be and how it would come together. All right.